Hey, welcome everybody to our group meeting, open group meeting or affiliate meetup today. And yeah, before we start with the actual content of today, I just want to uh, briefly take the time to acknowledge the support that we get from different funding agencies. So this activity is partially supported by the Research Council of Finland via the project, A Mathematical Theory of Trustworthy Federated Learning, and a similar project is also funded by the Janne and Atos Ergo Foundation. So we are very grateful for the support. We also get a bit of support or some financial support from the Business Finland project on forward-looking AI governance in banking and insurance. So I just want to point that out that our activities, including this activity, is supported by these funding agencies. Okay, and yeah, today we have the great pleasure to have Virve Karsisto from the Finnish Meteorological Institute telling us about post-processing road surface temperature forecast with XGBoost, which is a very timely topic given that soon we will have again frozen roads. So thank you, Virve, for taking the time and please take it away.
Yeah, thank you. If I first introduce myself, so I have been working in Finnish Meteorological Institute like over 10 years now. I started my master's thesis with road weather forecasting and then I did my PhD about it and I am still continuing with it. And this is a process I have been doing this year about post-processing or road surface temperature forecast. We are trying to kind of improve it with some machine learning-based modeling. But first, I introduced like basic things about road weather forecasting. So we are making it with a numerical model called RoadSurf. And in road weather forecasting, this near zero temperature range is especially important. We don't care about if the temperature is 20 or 30 or something like that, but in near zero, we are very interested even in small errors in our forecast. And if we can make our forecast right, then the roads can be salted in right time and there won't be any ice and unnecessary saltings can be avoided that are harmful for the environment and took unnecessary resources. Yeah, and the basis of forecasting are observations. So there are about 400 road weather stations in Finland. You can see them on the map. So in the north, not that many, but in the south, there are quite many, especially on these biggest roads. And road weather stations look something like in this figure. So there is this kind of pole at the side of the road, and then there are different kinds of measurement instruments there. And also we have road cameras where we can monitor how the road surface is actually looking like. And we don't get them at the moment, but it will be possible to get also observations from cars. And the road surface temperature is kind of the most important for us. And usually there are this sensor embedded on asphalt surface, like you can see on the left. But there are also these kind of optical sensors. This sensor is actually, I think, measuring friction and how much there is like snow and ice and water on the road. But there are also instruments for measuring road surface temperature like that. Yeah, and about our road weather model, it has been running in FMI, I think at least 25 years now, and it's based on this heat balance equation and heat transfer in the ground. It calculates it in one dimension only, and things that affect the road surface temperature are radiation, like short wave and long wave radiation, and the heat exchange between the air and ground surface. So the temperature difference between air and the ground and the wind speed affect to this. And then there is evaporation and condensation and rain and snow, which affect to the how much like water and ice and snow there are on the road. And then the model calculates how the heat is transferred one-dimensionally in the below the asphalt and in the ground. And as output, the model calculates this road surface temperature and tries to give an estimate how slippery it will be and if we need to be careful when driving. Yeah, and because road weather model does not calculate this large-scale weather by itself, we need input from this three-dimensional numerical weather prediction model, like these very big models that take a lot of computational resources to run. And as input, it needs air temperature, humidity, wind speed, precipitation, and radiation. And as output, well, I told this already, but road surface temperature and how much water and snow and ice there are on the road are the basic outputs. And more about this numerical weather prediction model data. So road weather model is kind of very sensitive to it. So if there are errors, they affect our road weather forecast too. And in this study, we used forecast from this MEPS that comes from Metcope Ensemble Prediction System. And it's run in cooperation with Finland, Sweden's, Norway's, and Estonia's National Weather Institutes. Its horizontal resolution is 2.5 kilometers, and it produces kind of ensemble forecast where we kind of run the model multiple times by changing the kind of original values and some other parameters a little bit, so we get kind of ensemble how the weather could look like. But in this case, we take only the main member, so we are not doing probability forecast, but only deterministic ones. Yeah, and official FMI forecasts are actually combination of these MEPS, and there is a specific no-cast system and also the long forecast, like several days ahead, come from this ECMWF's weather model data. Yeah, and when we run our road weather model, there is first this initialization phase where we take least air temperature and other values from observation data in the hopes of getting a good starting state for our model. And then there is this forecast phase when these are taken from this NVP model, in this case MEPS, to get the actual forecast. And few words about this kind of coupling method. This is kind of important for this short range forecast. So this coupling is done when we move from observation to forecast phase. In this diagram on the left, this blue dot represents the observed road surface temperature, and this yellow line the simulated road surface temperature in the model. And if we see that this simulated temperature is kind of too much different from the observed one, then we can reduce the radiation by giving it some kind of coefficient. And we can test different coefficients by running this 3-hour period until we find a suitable one where we forecasted and observed road surface temperature match. And then we can use this given coefficient in actual forecast phase so that the effect gradually reduces as the forecast advances. And this figure kind of gives an idea how this works. First, the road surface temperature in this case was too low, so the model kind of increased radiation, but we noticed that it was way too much, and then it gave kind of reduced version of it, which was almost correct, and then this 4 option matched with our observations, so the model continued with that coefficient. Yeah, and this is kind of a good way to improve the forecast in kind of this 1 or 3 hours time. Yeah, here you can see an example road weather forecast. I'm actually not sure if this visualization system is in use anymore, but basically here one can select which road weather station one wants to look, and then it gives forecast for the location. So in blue line here is the air temperature, and the road surface temperature is in green line, and dew point temperature is on gray line. And kind of important thing to look is this how much different this dew point and road surface temperature are, because we can kind of estimate how probably it is that there is some kind of condensation and deposition of humidity on the road surface, making them slippery. And although the road weather model is kind of a one-point model, if we run it enough times to different locations in a grid, then we can get this kind of map forecast. And on the left here is the road conditions that comes out from the model. In this case, there is a lot of snow in southern part of Finland and some ice and partly icy. And based on kind of these, how much there is snow and ice, the model calculates this traffic index. In the middle, it describes how bad the driving conditions are, and also kind of wind speed and precipitation affect to this too, I think. Yeah, and on the right side there is the friction coefficient. So in the southern part there is really bad friction in this case. Okay, then we can finally go to what I have been actually doing in my study. So we have training data of 4 years from September to May, and we are excluding the summer months because we are not that much interested in that. And when tuning our hyperparameters, we all use this fall for course validation, so we always leave 1 year out and use other winters to kind of train the model, and 1 winter to see how well it works. And then we save this final winter period for final validation. Yeah, and we had 8 forecasts a day, so new one started every 3 hours, and the total number of data rows was about 230 million, so there were kind of a lot of data suitable for machine learning models. And as a method, we use this extreme gradient boosting. I assume many of you know more about it than I do, but the basic idea is to build kind of ensembles, I think, of these decision trees. And that are kind of sequential, so the sequential decision tree tries to always correct the errors of the previous tree, so we get the better forecast. Yeah, and this slide shows the input data for our model. We have different weather parameters from this MEPS and VP model. This clear sky ratio means kind of how much radiation there is compared to clear sky radiation, gives kind of estimation of cloudiness. And the temperature gradient was the temperature difference between air and road surface. And then I had some time variables and location, and the actual target of the model was the forecast error, so the difference between observed and forecasted road surface temperature. Yeah, and I trained two model versions. The first was kind of this general model trained to work in all kind of temperatures. And then I trained this near zero focused model. So because we don't kind much care if our forecast error is big during springtime when it can be like 20 degrees Celsius the temperature, and the errors can be really large. So we didn't want to give too much kind of credit to those and make the model focus on correcting these forecast errors near zero. That is actually the most important thing. So I used this kind of weight function that was dependent on the observed road surface temperature and the lead time. And the lead time means how much far ahead we are forecasting, like if it is 6 hours or 1 day ahead from current time. And to verify this kind of this near zero focused model, I used this kind of musket mile, and only cases where observed temperature was between -3 and 3 were included in that. And also when the forecast lead time was 12 hours or less. Yeah, and then I somewhat explain my training process. So first I did some hyperparameter tuning. I noticed that the most important parameters were this kind of depth of our 3D and how many there are. And on this you can see on the x-axis the number of trees, and on y-axis is the average of this mean absolute error of our XGBoost model, and on different colored lines are this maximum depths of the tree. And when I did this, I used this fourfold cross-validation, so leaving one winter out and doing training with 3 and then validation with the one that was left out. Yeah, and here they kind of start nicely to, or the error stops to reduce around this 100 trees and maximum depth of, actually, no, this is on the way, but six, yeah, so maximum depth of the trees was 6. So this circuit with red was chosen as the values I used. And then I made some test with this weight function, so which parameters work best. So this K steeper decrease in weight with lead time if we have large scale, and this sigma affected to this temperature, so less steep decrease in weight with temperature. And in these figures, there is on the x-axis is this lead time in hours, and on the y-axis is the observed road surface temperature. And we run our XGBoost correction and compared it to kind of, or we run the XGBoost with weights and without this weighting, and then took the difference to see how much big an effect this weighting has on this mean absolute error. And red values tell that the weighted model works best, and blue values that the kind of this model without weights is better. And on these right figures, there is the actual weight. So near zero, there is more weight, and then this gradually decreases as lead time goes on. And also near zero, it is there is bigger weight than when we go to up and down in temperature. And in these upper panels, there is kind of gradual decrease in this weight, and also we can see kind of light or small temperature or small increase in this mean or model performance. So yeah, but on this lower figure, there is kind of the lead time doesn't affect the model weight that much, but there is a much deeper kind of decrease of the weight by temperature. And here we see that the near zero, the improvement with weights is kind of big, but on the other hand, out of this zero rand there, it actually makes it the forecast worse. But actually, overall, when we took like calculated this musket mile, so we took on temperatures near from -3 to 3, then this kind of more steeper decrease by temperature and giving almost equal weight to different lead times kind of worked better than this upper one. Yeah, here is a figure where we tested kind of these different parameters for sigma and k, different colors, so different k values, and on x-axis there is this sigma, and on y-axis this musket mile, so only temperatures from -3 to 3, and the best results were where this k was really small, so the lead time didn't really matter to the weight, and when sigma was 3, so it was still quite steep decrease in or increase in or well, near zero get very much weight more compared to the other temperatures. Yeah, and then we made some features importance tests. So we did three different kinds of tests. One was this forward selection, then backward elimination, and then this sub-analysis. And this number here is the average rank of each parameter from these tests. And on the left, there is this model without weights, and on the right, the model with weights. And an interesting thing is that for this general model, the cosine time of the year was clearly the most important one. So our model error is clearly dependent on the time of the year. But for this model that focuses on zero ranks, this time of the year actually made the model performance worse. So these were actually excluded from the final version. And this might be because they kind of make the kind of wrong correlations in the model, I think, because the temperature is not that always kind of, or it depends on the time of the year, but there can be low temperatures in spring and too. Yeah. And also important variables for this general model were global radiation and latitude and temperature gradient, whereas for this model with weights, there were long wave radiation was rather important, and this cloudiness describing parameter clear sky ratio and wind speed and road temperature. Yep, and then I did this hyperparameter tuning again for this vected model. So, and this time the kind of my just kept decreasing and decreasing, but I wanted to avoid kind of overfitting it, so I decided that this an estimate as 100 and max depth of 10 was enough for purposes. And to tune other hyperparameters, I used this Optuna that kind of charges different parameters. and changes them on the run. And I did 100 trials and used again this four-fold cross-validation. But this actually wasn't able to improve the model performance at all for this weighted model, and there was only little improvement for this general model. So I used the on default values for this weighted model, and for this non-weighted model, I actually took the parameters from, I took these Optuna optimized parameters, although they didn't improve the forecast that much, but they were a tiny amount of better. Okay, then an example forecast. On Loviisa road weather station, on the red line, there are these road surface temperature observations, and on dark blue line, the original forecast. And the lighter blue line shows the correction or the corrected forecast with this general XGBoost, and this violet line, the correction with this zero optimized model. And we can see that it kind of produce kind of sensible time series, so it's not jumping up and down, which is kind of good. And in this case, it actually makes the forecast closer to observations too, which is nice. And few words about verification of weather forecast. So this XGBoost, when it verifies its result, it gives just one number describing like the full dataset, but in weather forecasting it is not nearly enough because there is a lot of variation depending on different things. So first there is this lead time. So usually if we forecast from 2 days ahead, the forecast is worse than when we are forecasting only 2 hours ahead. And then time of the year matters. So usually we get better forecast during winter time when there is less variation in temperatures than during the springtime when the sun can heat the asphalt very hot, and it's different to predict exactly how hot it is. And yeah, time of the day, because there is more radiation during daytime, so it affects our forecast. And also forecast location, kind of local factors can affect the road surface temperature. And this figure below just kind of tries to describe how we have kind of make one forecast every 3 hours. So there is time on the x-axis and temperature on the y-axis, and this red line shows the forecast. These are just random examples, but forecast kind of that is started at 0 UTC, and then we make new forecast at 3 UTC and new forecast at 6 UTC and new forecast at 9 UTC, and they can each kind of give a different results. And so when we are do verification by lead time, we like look only at the start of the forecast and calculate how many hours ahead the forecast is. And it kind of can be very different if we start from midnight and forecast from the midday where the lead time is 12, rather than when we start at noon and make forecast for midnight. So the lead time is the same, but the kind of forecast situation is totally different. So the results can vary a lot. Yeah. So, but here are kind of overall results by this lead time. Anyway, although I say it's bad, but it gives kind of some general look of our model performance. So there is on continuous lines this mean absolute error, and on dashed lines this mean error. And this dark blue line is the original model, and violet line is the XGBoost corrected version that is focused on zero range, and on the light blue, the general version of the XGBoost model. And we are happy to see here that the XGBoost correction really improves our mean absolute error quite considerably. And because they are kind of calculated over all temperatures, this general model works a little better than this zero-focused model. And then when we look this mean error, we can see that the original model is actually closer to zero, but that is only because there are kind of equal amount of forecasting too high or too low temperatures, so they kind of cancel each other out. And this is similar figure, but it shows the masked score, so only for temperature range from -3 to 3. And in this case, this XGBoost correction with weights works so much better than this general correction here. But the mean errors are almost similar. Yep, and in the previous slide, we looked at only results separated by lead time, but now we kind of expand it to the time of the year, so different months are shown separately here. And upper panels show this mean error, and lower panels this mean absolute error. And the panels on the left show this kind of XGBoost corrected errors or corrected model, and on the middle there is the I think the original forecast. And then on the right there is their difference. So the darker the color is, the better the kind of the XGBoost makes the forecast. And well, we can see here that during winter time the errors are generally less, but there is still kind of nice improvement in this mean absolute error. And in springtime the errors are larger, and also the kind of improvement is also larger here. And we see that this mean error shows that still our forecast is too warm kind of a lot of the time, but the correction is able to reduce this bias here. Okay, then we go to more advanced verification. So last figure showed this x-axis on lead time, but now we separate it by this time of day. And then there are different lines for forecast that are kind of started at different times of the day. And our panel on the left, there are results for December, and on the right for March. And the continuous lines are again this mean absolute error, and mean errors are on the dashed lines. And the lighter colors are these forecast corrected with this, I think this is the general XGBoost model. And the darker colors are the original forecast. And as we can see, the mean absolute error is somewhat lower with this correction for every forecast, which is quite nice. And also this mean error is showing less positive bias, which is good during December. On March, where there is more radiation during daytime, the results are more complicated. So during daytime, we usually have a larger forecast error because of asphalt heating up. But this XGBoost is able to reduce this error too. And where we look at this mean error, the XGBoost kind of improves the forecast during this kind of from midnight to morning, but during daytime there is not that much difference. Yep, and we can also look for kind of forecast for different stations. So here are again kind of overall scores for when we combine the data for the full year and for kind of all times of the day, but here is the lead time of 3 hours, and this time the Corel shows the percent of improvement, like how many percent better our forecast is compared to the original one. And on the left there is this general kind of general mean absolute error, and on the left there is this masked and results for this weighted model. And as we can see, this general model improves this general score at every roadway station, which is nice. And the improvement is even larger in case of this kind of masked from -3 to 3. But there are actually 2 stations where the results were actually worse for some reason. But in general, it works really well. Yeah, and then about some future plans we have. So these results were more deterministic road weather forecast, but we are also doing probabilistic ones, like how certain it is that the road is freezing or not. And these are done based on these ensemble forecasts. So we run our road weather model with this MEPS ensemble, so separately for each MEPS ensemble member, and get this ensemble road weather forecast. And this shows an example how road surface temperature can vary in different ensembles. And here we can see the spread is large. There is a lot of uncertainty in the model, and when they are kind of close each other, the forecast is more certain. But these kind of probabilistic forecasts still will need some improvement. I am not kind of satisfied with them, so I have plans we could use some kind of machine learning, like gradient boosting EMOS or something like that, to improve them. And I actually just submitted a funding application to Research Council of Finland about this project. So let's see if I can get the money. Okay, but by summary, the overall scores were reduced depending on the lead time by 3 to 23%, and on this range from -3 to 3 with lead time to 12 hours, the improvement actually from 17 to 34%. This is considerable improvements. But it needs to be remembered that the results vary by time of the year and time of the day and location. Yeah, thank you for listening. Do you have any questions?
Thanks a lot, Virve, for this excellent presentation about a very interesting machine learning application. As I always say, I consider weather as the mother of all machine learning problems, just from the amounts of data you have to process or you could use, and the highly nonlinear relations between the relevant variables. So, yeah, my first question would be a quite practical question. Why do you use mean absolute error and not mean squared error?
Yeah, I think because it kind of root mean square error gives more weight to these big errors, and they usually occur kind of this when the temperature is like at 20 degrees of Celsius, and we don't like them to affect too much our score. So that's why I use this mean absolute error.
So it's what I always like to explain. It's the statistical properties of the absolute error loss. It doesn't emphasize so much outliers.
Yeah.
Yeah, very good, very good. So this I can now use as a convincing example for students to use. Sometimes it's better to use absolute error loss instead of squared error loss. On the other hand, it makes the training harder, I guess. So this training takes some time and computational resources, as you pointed out.
I don't remember its name, but I used this kind of combination of this. Was it some kind of mean Hooper or something?
Yeah, yeah.
So
Okay.
that worked better.
Yes. Are there any other questions? I have many more, but I let the audience now ask. You can now unmute yourself. Okay. Maybe later. Now, my next question would be a very tricky question. I'm sure there is no answer, or I would be very surprised. How do you know what is the fundamental limit? How well can you forecast, let's say 3 hours ahead, the road surface temperature? Is there a physical fundamental limit?
Yeah, well, I don't know.
Yeah, I also don't know, and I'm wondering, in general, do you know works that study physical limits, intrinsic limits of how accurate you can forecast weather 1 day ahead? I guess this depends on the mathematical models that you use. If you use a continuous mechanics model, or if you just look at the raw data, so you look at all the weather observations and try to figure out what are the fundamental limits of the accuracy.
Yeah, I think there are probably kind this of
Yeah.
studies, yes, kind of these, at least these based on some theories or
Mm,
something.
mm.
But yeah, I don't currently remember their name, but
Yes, and related to this, of course, is the question, if you don't have a fundamental limit, which is often the case, as it's based on observed data, how do you know how far you don't know how far you are from optimal, so you in principle cannot say if you solve the problem ultimately. So your improvement
mm,
is the final step, and there's no way you cannot improve it. And for example, how could you decide, or how do you now decide if you want to use more data? You mentioned, if I understood correctly, you want to use data collected by cars, by private cars, or some cars that the Meteorological Institute sends around.
yeah, I think many current car manufacturers are kind of selling their data. So we could use that, but actually we are not buying it at the moment.
Very interesting. So the car manufacturers become data providers like Facebook and social networks.
Yeah.
Their core product is data. So interesting. So Mercedes or any other car company, they become data providers or data collectors in reality. Yes,
Yeah.
there's a question by Miko.
Yes, about the yeah. First of all, can you hear me?
Yes.
Yes.
Yeah, good. Actually, I wanted to answer about the theoretical limits because there's the butterfly theory. The defines the limits of the the forecasting. That's actually where the whole theory was invented. Was for the how like what is the theoretical limit for weather forecasting, and that might be a cause can be they used to calculate like the theoretical limits, although they are of we cannot get anywhere near them at the moment. So
Yeah. Yeah, but do you know if I heard about this butterfly effect or this, but is it really practical, this theory? So I just came across, I searched a bit for a paper from the 60s or 70s, and as I understood, these studies are based on a mathematical model, like a physical modeling of the atmosphere. But how useful is this? I guess you need to collect a lot of data to run those models to get these fundamental limits. Yeah, there's another question by Tapio.
Yes, thank you for the excellent presentation. Have you been considering using any Earth observation data, so any like thermal infrared images or something like that?
I think that the roads are kind of too tiny to get the temperature very accurately from these kind of images.
Okay, very good. Yeah, just to reiterate about this, you said you thought about buying this data from car factorers. Uh, do you think what's your intuition? Might this help a lot, or might it be more useful to set up this more expensive, more precise? As I understand, you use some radio waves or spectroscopy. So you radiate electromagnetic waves on the surface and you measure the reflectivity, or at least I remember something like this can be done. Do you think it's more useful to install more of these high-end measurement stations?
Well, it kind of depends which kind of sensors these cars have, because I'm not exactly sure if they are actually measuring the road surface temperature. Many times there is only this air temperature, and that is really not that useful because the air temperature near the car can be kind of different than the road
Mm,
surface temperature what we are interested in.
mm, mm,
But if the car would be equipped with these kind of optical sensors that measure the surface, that would be
mm.
actually really good.
Yeah.
But in general, I think cars will be more effective,
Mm,
than like installing a lot of these
mm.
individual stations.
Well, and this, of course, if you have political power, like in Finland, the authority could say every car that is licensed that is allowed to drive in Finland must have such an optical sensor and must share their data with the Finnish Meteorological Institute.
Yeah, that would be nice.
But this goes now maybe a bit too far.
Yeah,
Okay.
because this road surface temperature can vary a lot even on different lanes on the road. So we
Yeah,
could
yeah,
make really accurate forecast if we had any observations.
yeah. So do you also take into account I mean, naively, I would think you can predict pretty well when you know the humidity, you know the temperature, you know maybe even the local geometry. You know if there's a forest nearby, as I understood, having a forest nearby changes the microclimate, or it's like a microclimate prediction problem. But what in this case you also have to take into account the material of the road. So
Yeah.
do you take those also into account, like the recipe of the asphalt?
No, actually, we have just kind of general parameters, and they are same for the full country. So
Mm. Yeah.
they are just parameters that work well on average.
Mhm, mhm. Very good. Was there another question? Please ask if anybody else has a question or a comment on the chat. Yeah, there's a question. Is there a need to run regression to categorize the results to certain criteria? Winter tire, summer tire? I don't know. I don't understand that question really. Maybe you could open up a bit more.